Hello everyone, and welcome back to another quiz tutorial. In this quiz, we're going to be discussing the concept of linear maps. And if you guys have already seen the lecture videos on this concept, you guys may already know that this is a pretty beefy concept. There's a lot to go over, and this quiz is going to be no different. The quiz ranges from finding the components of a matrix after a change of basis, all the way to eigenvalues and eigenvectors. And all these are going to be important, and I guarantee that each one of these concepts will be on your midterm. Now, good news for you guys. The concepts are actually very, very easy to understand, and the formulations are even easier. So I'm hoping by the end of this video, you guys have a good grasp on everything, and you guys will be really confident heading into the midterm. So before we begin, as always, we're going to go through the theory. Usually I like to keep it to one slide, but as we have a lot of concepts, there's actually a couple slides we're going to go over, but it shouldn't be too bad. So with that being said, let's jump into the theory. So the first topic we're going to cover is change of basis. So you guys may remember change of basis because it was basically quiz number 7. Now we're going to talk about it and we're going to kind of add on to it a little bit, show you guys something new. So this is review from quiz 7. If you guys have questions, I highly recommend you guys go back to quiz 7 because this is going to be more of a crash course. But let's say we have a vector u, which is in terms of e1 and e2. And we say, well, this is great. But what happens if I want to rotate e1 and e2 to get e1 prime and e2 prime? Think of this as I'm changing my coordinate system. And the question that we dealt with in quiz number 7 was, what are the new components of u prime? So notice in these two pictures, the vector u did not change locations, we changed the coordinate system. And we said, okay, well, this is done through a matrix Q, which we call the rotation matrix. And determining the components of Q, we use this formula right here. So again, I went through this all in quiz number 7. If you guys have questions, I highly recommend going back. But we concluded that if we're rotating our basis counterclockwise, it's basically just going to end up with this formula here, where we have cosine of theta, sine of theta, and then in the second row, we have negative sine theta and cosine of theta. And if we know our angle theta, which you guys are almost always given, we can easily find Q. And then we also concluded that the components of u in the new basis set, so that'd be u prime, is going to be equal to q multiplied by our original vector u. Now, that was quiz number 7. You guys should be experts by now. Let's go to something more fun. So we're in the original basis set, so we got e1 and e2, and we have our same vector u. But now let's define a second vector, the second vector v. And what v is a matrix transformation of u. So all we did is we took our vector u and we multiplied it by a matrix M. So this isn't a change of basis. We're finding this through a matrix transformation M. So now if we rotate our basis, you guys are going to see there's going to be a little bit of different things. We still have u prime in the same place as u, but of course the components are going to be different because we changed the basis. And we're going to have v prime, which will also have different coordinates because again we changed the basis. So now the question becomes, what is that m prime? That m prime that transforms u prime to v prime, because since we changed the basis, well, of course, the matrix M will also change. So that's the goal of quiz number 8. We're going to need to find that matrix transformation. So if we look at here, we know that v prime is equal to q times v. So this is right from quiz number 7, we discovered that. And since we know that v is equal to the matrix transformation of u, we can kind of expand on this formula. We can also get a second formula from the the right-hand side. I can't even tell my signs apart. Where we got v prime is equal to m prime u prime, and we can expand this out even further. So this is kind of theory. Don't worry about it too much. We can equate the two sides, and then in the end we get m prime is equal to q times m times q transpose. And I know a lot of you guys are going to say, wait a second. Shouldn't it be the inverse? Well, yes. But since q is orthogonal, the transpose of q is actually equal to the inverse. So the derivation, it's actually pretty simplistic. You guys don't need to know it though. Don't worry too much. If you guys want to figure it out on your own, by all means, go ahead. But I went through it fast because in the end, I just want to prepare you guys for the midterm. And for the midterm, that's all you're going to need to know. So if it gives you a matrix and it does a change of basis like we had here, and it says find the components of the matrix in the new coordinate system, we're just going to find this formula. We're just going to throw everything in there. And as you guys can see, it's pretty easy because the m, well, they're going to give you m. So the only thing we need to know is q. And we defined q back in the previous question. So q is also pretty easy to find. So the second topic we're going to talk about is invertibility. And this one's even easier than change of basis. So if you guys see an invertibility question, you guys are laughing. Nice, easy marks. So there's basically 3 things you're going to need to know. If a matrix M is invertible, the determinant of m does not equal 0. So it does not equal 0. The second one, m is bijective, and you guys already know that before, because remember we said if a function is bijective, it's also invertible. And then the third one is the kern of m, or the kernel, is going to be equal to the 0 vector. But for our purposes, this is the one we're going to want to focus on. The determinant of m does not equal 0. So how do we find a determinant? Well, in R2, here's our formulas. And then in R3, or I guess a 3x3 matrix, here are the formulas. I'm not going to go through the formulas. You guys have seen this in Eng 130, Math 102, and I think even Civi 395. So you guys should be very well familiar with these formulas. So all you guys are going to need to know, invertibility, we're going to deal with determinants, as you guys will see in the question set that we prepared. And finally, we have eigenvectors and eigenvalues. So the question in the quiz is actually a little bit more intuitive. So I'm not going to spend a lot of time here discussing the formulations of these because I'm going to go through that in the quiz itself. But all I want you guys to do is understand what exactly an eigenvalue and eigenvector is. So let's say that we have a vector u and it's in the basis set e1 and e2. And I say, okay, this is great. Let's perform a matrix transformation going from R2 to R2. And what we'll see is that our vector u can change direction as well as change in its size. So as we can see here, the direction of u changed. In addition, it became a little bit smaller. Now, when we're talking about eigenvectors, these are vectors that if we have them in the original basis set and we perform a matrix transformation M, what we'll find is that after the transformation, they'll maintain the same direction. So that's going to be the key here is if we look at that purple vector v, after the matrix transformation, the direction of v did not change. The size of it can change, but the direction does not. So we can say that since the direction of vector v does not change the direction after the matrix transformation, we can say that v is an eigenvector of matrix M, and it's associated with eigenvalue lambda. And that lambda is basically because even though the vector did not change direction, the vector did shrink. So the size did change. That has to do with the eigenvalues. So that concludes all the theory. I know it was a bit much. Again, linear maps, quite a beefy topic. We had lots to go over, but hopefully you guys have a little bit of an understanding so that when we attempt the quiz right now, you guys will see, oh, okay, that's what he meant by this, or oh, okay, that makes sense now. So with that being said, let's jump on into the quiz. All right, guys, welcome to the assignment. So as you guys will see, the quiz itself is actually 5 questions. I've combined questions 4 and 5 because they're almost the same question, and you guys will see that later. So we got 4 questions. It shouldn't be bad. It should actually take us really quick. So when I solve these, I'm going to go kind of in the midterm mentality. So I want you guys to kind of think fast. We want to do these questions fast in the midterm. The questions are always straightforward, so let's try and do them fast. So if we look at question 1, it says, consider the new basis set B prime, which is composed of vectors E1 prime and E2 prime, where the new basis vectors are 30 degrees counterclockwise from the original basis vectors E1 and E2. Determine the components of the following in the new basis system. So part A, we have a vector, and part B, we have a matrix. So really quick, I'm just going to come down here because we discussed in the theory that in order to get the components of something in the new set, which we defined as something prime, we use the following formulas. So for a vector, if we want u prime in the new basis set, it's going to be q times u. So this is very, very simple. All we need is that matrix q. Nice and easy. Similarly, for the matrix, and I guess I'll switch to pink, m prime can be found using the formula q times m times q transpose. So of course, would it be nice to memorize how these are derived? Of course it would be. And should you guys memorize them? Well, probably not. You guys can probably get away without them. So if you guys remember these formulas, it's basically just plug and chug. The only thing that you guys are going to have to realize is, okay, well, I have u, so that's good, and I got m, that's good, but I don't have q. One thing that is nice is q is the same for both of them. And q is that rotation matrix that the basis vectors are rotated by. So if we look up to the question, it says that the basis vectors are 30 degrees counterclockwise. And it's very important to note not only theta, but also the degrees. Theta and degrees are the exact same. I'm talking out of my ass. What is very important to notice is what direction is being rotated. So in this case, it's counterclockwise. So in the midterm, you guys can actually derive the Q matrix quite simply But what I recommend doing is saying, okay, well, if we're in two-dimensional space and we have a counterclockwise rotation, so that's the key, a counterclockwise rotation, Q is always going to be the same. It's going to be cosine of theta, and the second component is going to be sine theta. And on the bottom, we have negative sine theta. And then over on the other side, we got cosine of theta. So again, it's important to recognize this is for a counterclockwise rotation. If this was a clockwise rotation, this is not the same. So you guys need to remember that. It changes depending on if it's counterclockwise or clockwise. But you guys will find that out in the assignment. What I recommend is in the midterm, just bring in Q for clockwise and a Q for counterclockwise. You guys will be good to go. All right, so since we know this and we know theta, all we have to do is substitute theta into this matrix, and then we get all of our values. So at the top here, we got 0.866, and it's going to be on the bottom too, 866. And then the sine of 30 degrees, well, that's 0.5, so we're going to have 0.5 here, and then negative sine, so we're going to have negative 0.5 down there. So we have Q. And as mentioned before, that's all we needed because we already have M and we already have U. So if I'm looking at U, we know that U is going to be Q, which we already have, times the vector U. And when you go a 2x2 matrix multiplied by a column vector, what you guys will end up getting is another vector, which makes sense because U prime should be a vector. And sorry, I should put U prime there. So if you guys throw all those in together, and just do it on your calculator, don't try and solve it by hand, you get 1.366. And in the bottom, you get 0.366. So it's as simple as that. I did a bunch of talking, but if you guys were just not do as much talking and just go right at it, you guys can solve this pretty quick. So that's why these midterm questions are nice. All you had to do is throw in numbers to find Q, and then multiply Q times your U to find U prime, which is part A of the question right here. So now, the second part, which is new to this quiz, which we didn't do in quiz number 7, is we need to find the matrix components. So it's just as simple. Since we already knew Q, we know that the new components of the matrix, which we call M prime, is going to be Q times our original matrix M times Q transpose. And again, Q is orthogonal. So if you guys really wanted to, really feeling daring, you guys can go Q times N times Q inverse. So they're going to be the exact same thing because, again, Q is orthogonal. So again, just throw it in your calculator. No one cares. No one's going to look at your work. It's a multiple choice test. As long as you circle the right answer, you're good to go. So all you do is define Q in your calculator, define M, throw them all together, and then you should get something that looks like this. So my first value, I got 1.866. And then below that, I got negative 0.5. Going to the second column at the top, I got 1.5. And below that, I got 0.134. So it's as simple as that. Even though the theory, I probably butchered it because I was going through that a little fast. You guys can see that solving these problems, it's not that hard. So I'll go up. We solved two different situations. All we had to do was find Q. And again, just write them down on a cheat sheet. Who cares about the derivation? And then you just have to multiply them by either A, your vector, or B, your matrix. So good to go. Now, the second question, which is also an easy question. As you guys will see, this course is always so complex. It sounds terrible, but the questions are actually pretty simple. And that's just due to the generosity of Dr. Deep. He's very, very kind. But the second question, it says, which of the following matrices are invertible? Again, such a standard question. You guys will definitely see this on the midterm. And what we have to realize is that when something says invertible, we have to think of one thing. The determinant of that matrix, so the determinant of M cannot equal 0. And if the determinant does not equal 0, then yes, it's invertible. So I'm just going to put a little arrow here and go invertible. So it sounds like a scary question, invertible. You're thinking matrices, ooh, 102. Well, I hate 102. Nope. Here it's nice and easy. We just have to find the determinant. If it's 0, then it's not invertible. If it does not equal 0, then it is invertible. So for a 2x2 matrix, the determinant's pretty easy. In this case, we have the determinant of M is going to be equal to 1 times 1 plus 0 times 0. And if we do the math here, which is pretty complex, we find out that the determinant's equal to 1. And since 1 is not equal to 0, then yes, this one is invertible. So I'm just going to put I there for invertible. I'm just too lazy to write it out. You guys already know by now I'm lazy. So we can move on to part B. Same scenario, same situation. So we can find the determinant of m again. And in this case, it's 1 times 0. And this is already kind of showing you guys what it's leading to, plus 0 multiplied by 10. And in this case, we find that the determinant is 0. So since the determinant is 0, we can conclude that this matrix here is not invertible. So I'm going to go not I. And again, I just means convertible. Convertible, no, I'm not talking about the car. Invertible, I'm losing my mind now, guys. The long weekend was not kind to me. Hopefully you guys had a nice long weekend, though. All right, moving on to part C, we're going to have the determinant of m. So again, it's the exact same scenario, and it's the same in 3D. You just find the determinant. So in this case, we got 1 times 10 plus 5 times 10. Or sorry, why am I going plus? You guys are probably thinking I'm an idiot. This should be minus, guys. All right, coming up here. Oh, yeah, I messed up on all of them. I bet I was just driving you guys crazy. You guys following along at home. All right, so the first one is going to be 10, and we minus 50. So the determinant here is negative 40. And even though it's negative, like a lot of people say, oh, negative, that must mean something bad. Nope, it's still good to go because it's not equal to 0. So in this case, this one is invertible. I just about said convertible again. All right, so the last one, just kind of round it off, we can find the determinant of m. And this time I won't mess it up with the plus sign. I'll make sure that there's a negative sign. So we got 1 times negative 20. And we go minus, see, I can get it the second time, minus 10 times 2. So we go here, the first one's negative 20. And we go minus, and the second one's also negative 20. So minus minus is positive. We find out that the determinant here is indeed 0. So in this case, this one is not invertible. So if you guys are on the midterm, you guys see a question, is the matrix invertible? You guys should just start laughing like, oh, is it invertible? Oh, that's an easy question. Just find the determinant. If it's equal to 0, then it's not invertible. If it is equal to 0, wait, even I'm getting mixed up in my head. If the determinant is equal to 0, it's not invertible, just like we had in part D here. If it's not equal to 0, it is invertible. I don't even know. I'm getting confused in my head. Hopefully that made sense. All right. So moving on, it says, let M be a two-dimensional matrix whose kernel contains only the 0 vector. So one other way of saying that is the kernel of M is equal to 0. It says, which of the following is true? And this is when you guys have to think back to Dr. Deeb's lecture. And he made it very clear that if the kernel is 0, so only the 0 vector maps to the 0 vector, well, then M is invertible. So if we look down here, M is invertible, well, that's right here. So this one's definitely true. Now, if you guys are like me, I would have circled B and moved on. That's a trap. Don't do that. So we have to kind of look at the other options just to make sure, because part C says M is bijective. And if you guys remember, bijective and invertible, they're basically the same thing. So this one's also true. So right then and there, we have two true ones. So if you guys were like me and circled C and carried on, you guys wouldn't be happy when you guys looked at the solutions after. So at this point, we can conclude that it's definitely going to be all of the above because we got two answers that are for sure correct. But if we look at part A, it says the determinant of M does not equal 0. Well, that's exactly correct because since M is invertible, the determinant cannot equal 0. So this is also a big fat check mark right there. So that's already talking about the invertibility of a matrix. Very, very simple concept. I just can't pronounce things right. So if you guys can understand my my jargon, you guys will be just fine. Again, nice, easy midterm question. You guys will be laughing. So now we're going to get into kind of the tricky one. And this isn't really tricky, but the way it's framed makes you have to have a good understanding of the theory. Most of Dr. Deeb's questions are very nice because They're just simple questions that follow a simple formula and you're good to go. This one's a little bit different because it wants us to find a two-dimensional matrix, so M is an element of M2, that does not have real eigenvalues. What does that mean, not real eigenvalues? Well, if you guys remembered math, and I forget which one because I hated math, we had imaginary numbers. The square root of -1 is equal to I, so that kind of crap, or it wants those non-imaginary stuff. So the questions sound simple. Find a matrix that does not have real eigenvalues. And then the second part, which is technically question 5 in your quiz, says, can a symmetric matrix have non-real eigenvalues? And this is going to be a very good question because I kind of rearranged this into a bonus question in assignment 2. So be ready for this one. So what I'm going to do is I'm going to do a little bit of a proof. If you guys don't like it, please skip ahead because this is going to get right into the proving sort of things. But let's say that our matrix, a two-dimensional matrix, just has arbitrary components. So what I'm going to do is I'm just going to say that M is equal to, oops, I don't even know what I'm doing. All right, hold on. Oops. I don't know where that came from. All right, so we're going to say that's M11, M12, M21, and M22. So this is a two-dimensional matrix. This is the case it wanted us to look at. So something like this. And it says, how can this have non-real eigenvalues? Well, we have to figure out how we find those eigenvalues. So if you guys recall, to find the eigenvalues, what we do is we take the determinant of, and what we're going to do is we're going to go M minus lambda I, and we're going to make this equal to 0. Now, the proof of where this comes from, that's in the lecture notes. You guys can find that really, really simply. Don't worry about it too much. All we're going to do is this is how you kind of find the eigenvalues lambda. So again, we're interested in lambda because we pretend that we already have M. I is just the identity matrix, nice and easy. So if we were to expand this out, we're going to get this right here. So I'm just going to put the determinant sign, which is kind of like an absolute value sign. It's going to be M11 minus lambda. We're going to have M22 minus lambda. So these come from the M minus lambda I. And then the other two components are just going to be the same. So this is going to be M12, and this one here is going to be M21. So this absolute value signs means that we're finding the determinant, and it must be equal to 0. So that's how we're solving for lambda. By taking the determinant equal to 0, we have our equation. We can solve for lambda. Now, the determinant here, it's a lot of fun to do. So the determinant of M minus lambda I, so this is exactly what we have above. We just take it the same way as before. So what we're going to have is we're going to have M11 minus lambda multiplied by M22 minus lambda, and then minus, and then the other side. So on the other side, we got M12 and then M21. And this must be equal to 0 right there. So that's just taking the determinant. And well, of course, we're going to have to do some math. So let's expand this out a little bit. So if we were to factor in the M11s and the lambdas and stuff like that and just make it one nice equation, we're going to get lambda squared minus, and then I'm just going to simplify this. We're going to have M11 plus M22, sorry, times lambda. So this comes from, lambda 1 times this one, and then the lambda times this one right here. You guys know how to do this. This is what, grade 11? Hopefully you guys know how to do that. I should probably add the hopefully because you never know. And then, of course, at the very end, we have M11 times M22. And then we finish it off with the minus M12, M21. And this must be equal to 0. So if you guys remember from, I guess, again, grade 11, this is a quadratic formula. And we can solve the quadratic formula by finding the roots by, the a squared and the b. I don't even remember what it is, but basically this is our a value. So in this case, a is 1. The second value in front of just the regular lambda, this is b. And then this third value, which kind of extends from here all the way to here, this is value c. So I'm just doing the quadratic formula and solving the roots of this function. So quadratic formula states that lambda is equal to negative b plus or minus the square root, so the square root of b squared minus 4ac, all divided by, and all divided by 2a. So remember, this is where we have to kind of go back to the question. The question says that, oh, let me get my highlighter out. It does not want real eigenvalues, so it wants imaginary eigenvalues. And if we come down here and look at this formula, and I better change the highlight color, the only way we can get imaginary values is if we take the square root of a negative number. So if we look at this formula right here for lambda, this right here is what we're going to be interested in. So to get negative eigenvalues, b squared minus 4ac, that has to be less than 0. And if that's less than 0, then of course we'll have negative eigenvalues. So what I'm going to do is I wrote this all down somewhere to try and expand it out. Oh yeah, here it is. All right, got nice fancy proof. So if we were to expand out b squared, so again b, I'll highlight it, and this is going to be b right here. Oh, I am losing my mind. All right, so this is b right here. It's m11 plus m22, but don't forget that there's also kind of the little negative outside. So if I'm expanding that formula out, what I'm going to have is negative m22, or m11, doesn't matter, minus m11 multiplied by negative m22, minus m11. So this right here, this is b squared, but instead of writing squared, I just wrote it out twice. And we go minus 4ac, so we got minus 4. If we look at a, well, the coefficient in front of the lambda squared is 1, so this is just going to be 1. And then c, well, that's kind of a little bit of a mess, so we got m11, m22, minus m12, m21. And again, in order to get the eigenvalues imaginary, this has to be less than 0. So what I'm going to do is I'm just going to do a quick little simplification. And what you end up with is m11 squared plus m22 squared, and then minus 2m11 m22, and then plus 4 m12 m21, and all this has to be less than 0. All right, guys, sorry for the weird cut. I was rambling on, so I thought, you know what, I better just take a breath and try and explain this a lot slower, because even this was confusing for me. I was I was on Google like there was no tomorrow trying to prove this. So if we were to look at this whole complete thing, the key is here that it has to be less than 0. So all those components have to be less than 0. And here's what we have to consider. This first part right here, if we add this all together, this will always be greater than 0. This will always result in a positive value, greater than 0. So if we were to try and make this whole thing less than 0, or make this whole thing negative, well then this right here, this is going to have to be a negative value. And it has to be a pretty large negative value. So this has to be a negative value. So again, this is to result in a negative eigenvalue. So if you guys want eigenvalues that are imaginary, then have m12 equal to, let's say, 1. And then what you can do is you can take m21 and you can make it equal to negative, and then make it just a really large number. So if you were to go negative 99, well, that'd make it a pretty large number. This whole thing would turn out to be negative. You get imaginary eigenvalues. So that answers kind of part 1 of the question. Can we have negative eigenvalues? Well, of course we can. How do we do that? Well, we make sure that m12 and m21 combine together to create a really large negative number. Because once they create a large negative number, then this highlighted portion right here inside the square root becomes negative, and the square root of a negative number is imaginary. So that's kind of part 1. Part 2, which is the really interesting part, and this will come back to your guys' assignment, is if we have a symmetric matrix, can we have negative eigenvalues? And just by looking at this, you guys are thinking, oh, well, Maybe? I don't know. Well, that's what I kind of thought. I don't know. But the answer is no. So I'm just going to write this right here. Oh, so you guys can all see. So a symmetric matrix has only real eigenvalues. So real eigenvalues. Ooh, that takes a long time to write. And how can we prove this? Well, if we go back up here, it's actually pretty simple. Remember, in order to get negative eigenvalues, we need this part right here to be a really large negative number. But if it's symmetric, M12 is equal to M21. That's definition of symmetric. So I'm just going to put symmetric. So if we were to look at that component right there, where we had 4M12, M21, and it's symmetric, well, this is just going to be equal to 4M12 squared, which will always be, and I was going to say never, but it should always be greater or equal to 0. There's no possible way to get that component negative. And if we can't get that component negative, then this whole statement above will never be true. And since that'll never be true, there's no possible way to get complex eigenvalues. So that really concludes this quiz/tutorial. I hope it helped. I know that my math proving is next to dog shit, but again, I hope it helped. So thank you guys for sticking around. I know this is quite a beefy video compared to most of them, but I appreciate it if you guys stick around. So this concludes quiz number 8. I will see you guys in quiz number 9.